All right, the last new section in 4.7 is L'Hopital's rule. It's a way of determining limits from indeterminate forms. So just a reminder, the very first unit we did this year was limits. And when we did limits, the first thing we tried to do was we tried to substitute our value into the function. And for this particular limit, we would get 9 minus 9, which is 0, over 9 minus 12 plus 3, which is 0. And that always told us, oh, that's an indeterminate form. We have to do more work. And so we did factoring. And we said, well, x squared minus 9 is a difference of 2 squares. So that would be x plus 3 times x minus 3. And the denominator looks like it's x minus 3 times x minus 1. And then the x minus 3's cancel because they're a whole. And so we get, plugging in 3 now, we get 6 over 2, or a limit of 3. And that was the way we did limits in the very beginning, before we knew how to do derivatives. There is a theorem that I didn't talk about then because you didn't know derivatives yet, but the theorem is called L'Hopital's theorem. And for L'Hopital's theorem, as long as you have an indeterminate form that is 0 over 0, so you're taking the limit as x goes to c of f over g, then that limit is equivalent to the limit as x goes to c of f prime over g prime. I would like to make a really big note here. This is not the quotient rule. We're not doing low-d-high here. We are just separately taking the derivative of f and the derivative of g and then reevaluating those limits. So this is not the quotient rule. This is the two derivatives separately, and it's a way of evaluating limits. I'll show you how it works with that same example that we just did on the previous slide. So we notice as we plug in 3 that we get 0 over 0. So we can use L'Hopital's rule. So we're going to take the derivative of the numerator, which would be 2x, and then we're going to take the derivative of the denominator, which would be 2x minus 4, and then we're going to plug in 3. So we get 6 over 6 minus 4 is 2, so we get 3. I think that L'Hopital's rule is a little bit easier than the factoring method that we did before. The only reason I didn't teach it to you in the first unit is because in order to teach it to you, I would have had to teach you derivatives, and in order to teach you derivatives, I had to teach you what limits were, so it's kind of an endless circle. The good news, too, is that you can use L'Hopital's rule when you have positive or negative infinity over positive or negative infinity. So it doesn't have to be 0 over 0. It could also be infinity over infinity. Those are the two indeterminate forms that you can use for L'Hopital's rule. If you don't have that, then you can't use L'Hopital's rule. So, for example, this one would be 1 over 0, which is infinity, over 1 over 0, which is infinity. So you could use L'Hopital's rule. I actually don't recommend that you do, but you could. Let's try it. We'll try it two ways. We'll try it with L'Hopital's rule. So since we can, we'll use L'Hopital's rule. This is the same thing if I rewrite it as x minus 1 to the negative 1 power. So when I take that derivative, I get negative 1, x minus 1 to the negative 2 power times 1. And this one would be negative 1 times 2x minus 2 to the negative 2 power times 2. And I get negative 1 over x minus 1 squared and negative 2 over x minus 2 squared. And it's just starting to look like a mess. Oh, so 2x minus 2. So it's looking like we wind up again with infinity over infinity. That just seems like it would take forever. And it's kind of a warning. You know, don't just be blind about this. Think about things. I actually think that there's an easier way to go about this problem. So I'm going to call this a dead end. L'Hopital seemed like a good idea. It's not. So if I am dividing fractions, 1 over x minus 1, that's the same thing as multiplying by the reciprocal. So I'm going to multiply by the reciprocal of 1 over 2x minus 2. Now I have 0 over 0, so now I can use L'Hopital's rule, and I have 2 over 1, which is 2. All right. Second example, I plug in 0, I get square root of 4, which is 2, minus 2, which is 0, over 0. So this is a really good candidate for L'Hopital's rule, so I'll go ahead and do that. So I have 1/2 x plus 4 to the negative 1/2 times 1 over 1. Now I plug in 0, I have 1/2 times, just a minute, Leo, square root of 4. So I have 1/4 for that limit. I want to remind you that before, when we did this problem, I taught you to multiply by the conjugate pair. So way back when we first started this chapter, this school year, you would have had to multiply this by square root of x plus 4 plus 2 in the numerator and denominator. L'Hopital's rule is much easier than that for this example. So we're not doing that. We're using L'Hopital's rule. All right, L'Hopital's rule even works if you're going to infinity. So I have the limit as x goes to infinity. I plug in infinity, I get infinity over infinity. So I can do L'Hopital's rule. The derivative of e to the x is still e to the x. The derivative of x cubed is 3x squared. I do the limit as x goes to infinity. I still get infinity over infinity. So I do it again. I still get infinity over infinity, so I do it again. And now I have infinity over 6, which is still infinity. And then the last example I have is just one that we proved it to ourselves using tables and graphs. We didn't actually evaluate this, but we didn't actually figure out this limit because we said we couldn't at the time. But oh yes, we did. We proved it using the squeeze theorem or the pinching theorem or the sandwich theorem. But here's a way to do it with L'Hopital. This is 0 over 0. Apply L'Hopital. So that's a 0. Derivative of sine is cosine. Derivative of x is 1. Plug in 0, and you get 1. So here's the nerdy math joke. If your limit is 0 over 0 or infinity over infinity, never fear, just drive it to the hospital. All right, that's L'Hopital, and good luck on your homework. And don't be mad that I didn't teach it to you before. I couldn't because you didn't know derivatives before.